Now let's do this with a numerical example. I have a 7 milliamp current source, a 2 kilo ohm resistor here, a 1 kilo ohm resistor there, a 4 kilo ohm resistor over there, and a 14 milliamp current source over there. Okay. Now this is a very simple circuit. You don't need to necessarily go through nodal analysis to find the solution to this. In fact, you can try superposition because it has two sources. I do strongly encourage you to do that, and when you solve it in let's say 2 or 3 different ways and find the same solution, you will have a lot of confidence in the answers. Okay, but we will go through nodal analysis because that's what we are trying to learn at this point. So first of all, for nodal analysis, it is more convenient to take the conductance values than resistance values. So this 1 kilo ohm resistor here, this is 1 kilo ohm resistor corresponds to a conductance of 1 millisiemens. Okay, and this 2 kilo ohm resistor is half a millisiemen or 1 by 2 millisiemens, and this 4 kilo ohm is 0.25 millisiemens or 1/4 of a millisiemen. Okay, now we need to set up nodal analysis equations, and let's choose this node to be the reference node. Okay, and I will solve for these voltages V1 and V2 at nodes 1 and 2 with respect to the reference node. Okay, so what is my set of nodal equations? I have the G matrix, which will be a 2 by 2 matrix. In this case, I have two variables V1 and V2, and that will be equal to the vector of independent current sources pushing current into nodes 1 and 2. Okay, so first of all, what is this entry? The very first entry here, that is the sum of conductances at node 1, which is 1 millisiemen plus half a millisiemen, which corresponds to 1.5 millisiemens, and this one, which corresponds to the conductance between node 1 and 2, is minus 1 millisiemens. Similarly, this one, which is also the conductance between nodes 1 and 2, is minus 1 millisiemens. We knew anyway it had to be like this because we know that the conductance matrix is symmetrical. And finally, the last one is the sum of conductances at node 2, which is 1 millisiemen plus 0.25 millisiemens, which is 1.25 millisiemens. Okay, and on the right side we have the vector of currents being pushed into nodes 1 and 2. What is being pushed into node 1 is minus 7 milliampere because 7 milliampere is being drawn out of it. So this is minus 7 milliampere, and what is being pushed into node 2 is plus 14 milliampere. Okay, and we have to solve this, right? Now let me rewrite these fractional entries in a different form so that it's easier to calculate the inverse. This can be written as 3 by 2 millisiemens minus 1 millisiemens minus 1 millisiemens and plus 5 by 4 millisiemens. This is not strictly necessary. Okay, you can of course work with decimal numbers, but here I am trying to do it without having to use calculators and so on. I will put it down this way. Minus 7 and plus 14 milliamps. Okay, so this is G and this is V and this is I. Okay, so now I have to invert this, and that's quite easy. I'm assuming you know how to do this. In another lesson, I'll discuss matrix inversion briefly, but for now, I'll assume you know how to do this. So the inverse of this will be 1 over the determinant of this matrix and for inverting a 2 by 2 matrix, we do this. Okay, and the unit of this, of course, will be kilo ohms. That is, I have not put any units over here, but the units of all the numbers will be kilo ohms. That's why I put kilo ohm outside. Okay, that's because the unit of each of these entries is millisiemens. The inverse of that is kilo ohms. Okay, or you can put it inside as well. The unit of the determinant will be millisiemens square, and the unit of each of these will be millisiemens, and millisiemen divided by millisiemens square will give you kilo ohm. Okay, and if you expand this whole thing, you will get 1 by 7 times 10, 8, 8, 12, all kilo ohms. Okay, so this is the inverse of the G matrix. Now, the unknown vector v1, v2 is the inverse of the G matrix times the current vector minus 7 milliamp, 14 milliamp. Okay, and this you can easily see is 6 volts and 16 volts. Okay, so the two node voltages turn out to be 6 volts and 16 volts. Like I said, you can do it by an independent method such as superposition and verify that this is indeed the case. Okay, so now we have set up the nodal analysis equations and solved for the unknown vector of node voltages. The rest of it is pretty simple, and usually in assignment problems and so on, you will not be asked to calculate every branch voltage and every branch current, but some specific ones which you can calculate using the voltages V1 and V2 which you already solved for. Okay, so what I now have is that this is 6 volts with respect to the reference node, which means that this voltage is 6 volts and similarly this voltage is 16 volts. Now it's quite common in circuits to point to one node and say the voltage at that node is something, let's say 6 volts. In those cases, it's understood that the other node is some implicit reference node, usually the reference node chosen for nodal analysis or what is indicated as ground in the circuit. Okay, a voltage is always measured between 2 points, so you have to be very clear about what the 2 points are when you specify a voltage. Okay, now the rest of it is very simple. The current source currents we already know, and the current through this resistor will be 3 milliampere. The current through that one will be 16 by 4, which is 4 milliampere, and the current going in that way will be 10 milliampere. Okay, and you can quickly check Kirchhoff's current law at each node and it will be valid. 14 milliamps is being driven from here, 4 goes this way and 10 goes that way, and out of that 3 goes this way and 7 goes that way. Okay, so this way you can solve for any variable you want in the circuit using nodal analysis. Okay.